All right, let's talk about 5.1 here. First, let's just get a little preview of where we're going. Now, this chapter is all about orthogonality and projections. Orthogonality is another fancy word for basically perpendicularness. Orthogonal basically means perpendicular, like just things that meet at right angles. And one application of that is that, like, if you have a point and you want to know what is the closest other point on this line, you don't want to go at like a 45-degree angle to get to the closest point on the line. You want to go at a 90-degree angle. So we're going to say that this point on the line is like the projection of this other point onto the line. And finding the closest point on a line to another point is actually very similar to finding the closest function of the form beta 0 plus beta 1 times sine of 0.7x to the points x1, y1, x2, y2, and so on. In other words, if you want to find what is the beta 0 and the beta 1 to model the set of red data points with the sinusoidal function of this form, it's kind of like trying to find the beta 0 and the beta 1 that makes the distance between the y1 through y20, if there's 20 points here, and the points on the sinusoidal function as small as possible. So it's kind of like finding what is the point in this two-dimensional subspace of R20 that is as close as possible to this given y1 through y20 point. You can't really picture that, and maybe it doesn't really make sense now, but that's where we're going with this. And you can imagine that, in science of all kinds, finding a model that describes your data, like a simple function like this that approximates what your data does, is a key idea. So we're going to see how to do that with linear algebra here. So that's where we're going by the end of the chapter. But for now, we got to lay a bunch of foundations. So 5.1.1, this subsection, this is going to be very familiar to you if you've studied dot products and worked with vectors in other classes like multivariable calculus or physics. So this is going to be a bit of a review, but it is going to be a little different. You should definitely sit through the video and take notes because we are going to be using linear algebra concepts of matrix multiplication to describe the stuff, maybe in a different way than you did in calculus or physics. So first, let's look at this definition, the definition of a dot product. We've already kind of talked about dot products when we defined like the row column rule. Like if you want to find row 1, column 1 of this matrix product, you just do the dot product of row 1 of the first matrix and column 1 of the second matrix. So we've already been doing dot products. So we're just going to sort of formalize that here. So the product u dot v is going to be a real number that you get by just multiplying u1 by v1, u2 by v2, all the way up through uc by vc, and add those all up. And the nice thing is that we can write this as matrix multiplication, just using the definition of matrix multiplication, all the way from chapter 2. And that means we can apply everything we know about matrix multiplication to dot products. Okay, so let's look at theorem 5.1 here. This says that u dot v is equal to v dot u. Now that should be kind of obvious because if you just look at the way this is defined, if you just change the order of the real number multiplication, you still get the same thing. So there's that. If you scale u by a scalar and then do the dot product with v, it's the same thing as k times that dot product of just u and v. Maybe that seems reasonable looking at the way the definition works. We also have a distributive rule. And also, u dot u is always going to be greater than 0, because u dot u is u1 squared plus u2 squared plus yada 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 plus uc squared. And the sum of squared real numbers is always going to be greater or equal to 0. So those are basic properties that we can use. We're going to define the length of a vector as, and we're using these like two absolute value bars. It's kind of the same idea as like the absolute value of like a number, like -3 is just 3, but two absolute value bars means that it's a vector we're talking about, to make the notation a little clearer. Anyways, it is the square root of u dot u, because u dot u is u1 squared plus yada 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 plus uc squared. And so this is basically just the Pythagorean theorem, or the distance formula, like we saw in warm-up number 2, part C. And we say a unit vector has length 1. All right, let's look at some properties of length. First of all, if you square the length of u, like just squaring this, that just cancels out with the square root, so you get u dot u. We're actually going to use this one a fair amount. And this is one of those things that might be different from the way you learned about the magnitude of vectors in physics or calculus, so definitely pay attention to this one. And also part 2 says the length of u is 0 if and only if that vector is the 0 vector here. Now, part 3 says that if you scale a vector by a scalar k, then the length of that result is the length of u just scaled by the absolute value of k. Why is it the absolute value and not just k? Well, because the length is always positive, even if k is a negative number. So like the length of -3 times u, for example, this is going to be an arrow that points in the opposite direction as u, but the length of it is still 3 times longer. So it's just 3 times the length of u, for example. By the way, did you notice that we've been talking about vectors this whole book, but we haven't defined the length of a vector yet? Kind of a different approach than in physics or calculus, where like the length of the vector is one of the first things you learn. But linear algebra is a little different. So anyways, let's do example 1 here. Find two vectors parallel. Anyways, let's do example 1 here. Find two unit vectors parallel to x. Now, first thing we want to do is notice that if you take any old vector x and multiply it by a scalar, which is 1 divided by its length, and then get the length of that, let's see what happens. We can use this property here, 5.2 property 3. It's just the k is 1 over the length of x. and multiply that by the length of x, like so. And the absolute value here isn't doing anything because this length is always a positive number. So we can just get rid of the absolute value bars here. And we can see that this is just going to cancel out, and you just get the number 1. So in other words, this is always a unit vector. Okay, so we can find one unit vector parallel to x here by doing 1 divided by the length of this x is, using the definition over here, the square root of 1 squared plus negative 2 squared plus 2 squared, that's 1 over the length of x, times the vector x. And that's all going to come out to be 1 over 9. This is all going to come out to be 1 over the square root of 9, also known as 1/3. So that gives you the vector 1/3, negative 2/3, and 2/3, like so. So that is one unit vector. But how do we get another one? Well, we could just get a vector in the opposite direction. That will still be parallel. Like if there was whether this was positive or negative here doesn't matter because the absolute value is still going to make it positive. So the second one is going to be the same as this, just with a negative here. Like so. And if you want to check that these are unit vectors, you could. And it will check out. The length of them will be 1. All right, so that's how you can take any non-zero vector and get a unit vector parallel to it. So now let's talk about the distance from u to v. Hopefully exercise 3, the warm-up, prepared you for this. But yeah, so when we say the distance from u to v, I mean like the point u and the point v. The distance from them is like the length of this line. And you can see that the length of that line is the same as the length of this arrow, which, well, this arrow is going to be v minus u, because when you do u plus v minus u, connecting them tip to tail, the u cancels out. So yeah, the length of that vector, v minus u, is the distance from u to v. Now, this doesn't just apply in R2 or R3 where we can draw pictures of them, but this also applies to R5. So here we have these two R5 vectors, u and v. So according to the definition, the length of v minus u is going to be, well, let's actually subtract them. We're going to do we're going to do v minus u, so that's 0 minus 1. 0 minus 0 is 0. The other zeros minus zeros are 0. And then we get to negative 1 minus 0 is negative 1 here. And then the length of this is the square root of negative 1 squared plus 0 squared plus 0 squared plus 0 squared plus negative 1 squared. And that just gives you the square root of 2. So length in R5 works basically the same way as length in R2. If you just ignore these 3 dimensions in the middle, this is the same thing as in R2, the distance from u equals 1, 0 to v is 0, negative 1. That distance is still the square root of 2. All right, so in the next video, we will talk about orthogonality, what it means for 2 vectors to be orthogonal. It basically means perpendicular. We'll see why, but we'll talk about it then. So in the next video, we will talk about what it means for 2 vectors to be orthogonal. The definition is that their dot product is 0, but it turns out that means that they end up being perpendicular geometrically. And we'll see why that is in the next video.